Hello students, welcome back to another video of matrix space. So we'll continue the example on continuous functions. So next example is let fix some x belongs to x, fix some x element of domain such that the function defined by f x of y is equals to distance between x and y is continuous. So x belongs to x, be a fixed element of domain, and function is defined on the rest of the elements such that distance between these two elements. So if we draw the diagram of this domain, then suppose this x is fixed element in that domain and function is defined, f is defined on this domain to again this domain to itself, suppose, then the function is defined as, suppose on this y is element of domain, then function is defined on this y as, just a second, so the function is defined as distance between these two elements. So function f x of y means this is the notation of function, x is fixed element, and f this on y is defined as, function on y is defined as distance between these two elements. Suppose this is another element of domain z, then the function defined on this z as distance between these two elements. So we have to show that this function is continuous function. There is no need to draw this diagram, just for the definition of function. So function is defined in this manner, and we have to prove that given function is continuous. We know that how to prove this function is continuous. We will take one sequence in this domain and prove the image of this domain is converges to, image of that sequence, such that, suppose we will take here, suppose yn is sequence, because y x is already taken here. So suppose yn is sequence that converges to 1, then we have to show that the image of that yn converges to image of y. So let this, there is no need to draw this diagram. Let x be a matrix space, let x be a matrix space, and x belongs to that x be a fixed element, be fixed, and therefore f is defined as f on x defined as function f on x defined as f of y, so that f x of y is equals to distance of xy, fxy is equals to distance of xy. So now we will take one convergent sequence in domain. Suppose let yn be a sequence in x, be a sequence in x such that yn converges to, suppose, y in matrix space x, yn converges to y. So we have to show that image of this yn, that is fx of yn, converges to image of y, that is fx of y. So our claim is fx of yn converges to fx of y, that is we have to show that, we have to show distance between these two elements in codomain is less than epsilon or very small. That is we have to show that distance between x and yn, f of xn is defined as distance between this x and y. So fx of yn is defined as distance between x and yn is converges to distance between these two, distance between x and y. So by triangle inequality, this all things happening in this matrix space, so we can use the triangle inequality. So therefore by triangle inequality, triangle inequality of D, we have distance between this x and yn, distance between x and yn can be less than or equal to distance between x and y plus distance between y and yn. Distance between x and y plus distance between y and yn. Distance between y and yn. Now we can rearrange this as, suppose distance between x yn minus distance between this, suppose xy. So we can write distance between x yn minus distance between this xy is less than or equals to distance between yn. To show that distance between x and yn converges to distance between xy means, by definition of convergence we have to show that distance between yn minus distance between xy is less than some epsilon. So by using definition of convergence we will say this converges to this. So here distance between xy and distance between xy is less than or equals to this distance between y and yn. Now we have to prove that this distance between y and yn is less than some epsilon. Then we will say that this is also less than epsilon. So by definition of convergence this will converge to this. So here we have this sequence yn converges to y. Since sequence yn converges to y in domain x, therefore by using definition of convergence we can write for epsilon positive, for some epsilon positive there exists n belongs to set of natural numbers such that distance between this y and yn, distance between y and yn is less than epsilon for all n greater equal n, for all n greater equal n. This is by definition of convergence. Since this yn converges to y, so distance between, that is elements of yn for all n greater equal n, elements of yn are very close to y, that is distance between y and yn less than epsilon. So this distance between y and yn less than epsilon we can write here. So using this equation number star we can write, therefore equation star becomes mod of distance between xyn minus distance between xy is less than epsilon. This less than or equals to this and this less than epsilon, so we can directly write this less than epsilon for all n greater equal n, for all n greater equal n. So this implies distance between xyn converges to distance between x and y. Distance of xyn converges to distance of xy by definition of convergence. So this implies, this means that this implies f of x of yn converges to f x of y, hence the given function is continuous. This implies the given, thus given function is continuous. Given function is continuous. Now the next preposition is so composite of continuous functions. Next preposition is, we know that the composition of functions, the composition of continuous functions is continuous. Composition of two continuous functions is also continuous. So this preposition can be written as, suppose let x, y and z, x, y and z be metric spaces, and let f from x to y be a continuous function. F from x to y be a continuous function at some x belongs to x, and g from y to z, be also continuous function, at some element of y, add some y, and the elements of y are of the form f of x. So add some y is equals to f of x. Then then the composite function, then the composite function g composite f. So first of all we have to apply f, so x to y, then we have to apply g, so y to z. So for g composite f from x to z, g composite f from x to z is also continuous, at some x belongs to x, at some x. So this is the composition of two continuous functions is also continuous. This is the preposition. Now we will see some examples on this preposition. So first example is, let f comma g are two functions from some metric space to R. Two functions from metric space to R be continuous functions. Be continuous functions. This preposition can be asked for multiple choice questions. Composition of two continuous function is continuous or not. So the next example is, f from x, f and g are two functions from x to real line, be continuous functions, are two continuous functions on metric space x, on metric space x, such that, so show that, not such that, show that phi from x to r square, show that phi from x to r square given by phi of x is equals to x to r square. So phi of x is equals to f of x g of x. So phi from x to r, so image of the elements is must be order pair, so f of x g of x. Show that phi from x to r square given by f of x is equals, sorry, phi of x is equals to f of x g of x is continuous, So here we have given f and g two functions from x to r are continuous functions. So f of x, if you take any sequence in this x, then image of that sequence under f or under g is also continuous. That is, suppose if you take xn, that xn converges to x, then if you take the image of that xn under f, then that f of xn converges to f of x. Also if you take that sequence under g, then g of xn also converges to g of x, because these two are continuous functions. We have to show that phi from x to r square is given in this manner, that is phi of x is equals to order pair f of x g of x, and we have to show this function phi is also continuous function. Now to show this phi function is continuous, we have to take one sequence in this domain, that is we have to take one sequence in x, and we have to prove that this sequence, suppose that sequence xn converges to x, then image of this sequence under phi, that is phi of xn must converges to phi of x in r square. So we will take one sequence in x. So let xn be a sequence in this x, xn be a sequence in x, such that sequence xn converges to x in domain, such that sequence xn converges to x in that domain. So our claim is this phi is continuous, that is we have to show that phi of xn is converges to phi of x. So our claim is phi of xn converges to phi of x, phi of xn is converges to phi of x in r square, So that is we have to show that phi of xn means phi of xn, phi of x is defined as f of x g of x, so phi of xn will be f of xn g of xn. That is to show that, we have to show that phi of xn means phi of xn is defined as f of xn comma g of xn, f of xn g of xn converges to f of x means f of x g of x, converges to f of x g of x in R square, in R square. So as this xn is a sequence in x, which converges to x, as xn is sequence in x that converges to x, xn converges to x in x, but we have given f and g both are continuous functions. So xn converges to x in x and f is continuous function, f is continuous function. Therefore image of this f of xn converges to image of this f, that is f, this implies we can write f of xn converges to f of x in R, because x to R, this x and this x both are same. So f of x in R. Also this xn converges to x in x and g is continuous function, g is continuous function. Therefore we can write g of xn converges to g of x in R, g of xn converges to g of x in R. So here suppose this is equation number 1, this is equation number 2. Using equation number 1, 2 and definition of product matrix, we can write, therefore from equation 1, 2 and definition of product matrix, we can write, therefore from 1 and 2 we can write the order pair f of xn g of xn converges to x comma 1, sorry, f of x comma f of 1 converges to f of x f of 1 g of x, sorry, f of xn g of xn converges to f of x g of x in R square. F of xn converges to f of x, g of xn converges to g of x in R. So there, by using definition of product matrix, the order pair f of x and g of xn converges to f of x g of x in R square. This is the solution of given example. Now the similar example is for your homework. Let next example, let f from R square to R be continuous function, be continuous function, then show that the map, show that g from R square to R, R square to R given by g of xy. So g is applied on R square, so g must be on order pair. G of xy is equals to f of x plus y comma x minus y. G of xy is equals to f of x plus y x minus y. This is order pair f of x minus y. Is also continuous. Is also continuous. G of xy is equal to f of x plus y x minus y is also continuous. Here f from x square, sorry, R square to R is continuous function, and we have to prove that g from R square to R is also continuous, but g of xy is defined on f such that f of x plus y comma x minus y. So to prove that this function is continuous, we have to take one sequence in R square. So if sequence in R square is must be of the form order pair, that is suppose x and y n be a sequence in R square such that x and y n converges to some xy, then we have to prove that image of that x and y n under g, that is g of x and y n converges to g of xy. That is we have to prove that f of xn plus yn comma xn minus yn converges to f of x plus y x minus y. but this f from r square to r square is continuous function, so xn be a sequence in r because order pair xn yn, so xn is sequence in r. So if we will just take the proof instead of giving it to homework, let we will take one sequence in r square. Let order pair xn yn be a sequence in r square such that that sequence xn yn converges to order pair xy in r square. Our claim is g of xn yn converges to g of xy. So our claim is g of xn yn converges to g of xy. That is g of x and y is defined as f of x plus y, x minus y. That is, we have to prove that f of xn plus yn comma xn minus yn converges to f of x plus y, x minus y. F of xn plus y and xn minus yn converges to f of x plus y, x minus y in this r, because f of x plus y, x minus y is, that is function f from r square to r, so this element are also the elements of r. Now as this sequence xn yn converges to xy in r, we can write xn converges yn converges to xy in r square, so xn converges to x, yn converges to y, as sequence xn yn converges to xy in r square. Therefore we can write this xn converges to x and yn converges to y in r. Xn converges to x in r, yn converges to y in r. So as these two sequences converges in r, so their addition, that is xn plus yn converges to x plus y in r. By this is from pre-analysis, that is on r. Addition of two convergent sequences converges to their addition of their limits. Similarly, xn, this is plus not equal to, minus yn is also converges to x minus y in r. Xn minus yn also converges to x minus y in r. So if we take the order pair of these two convergent sequences in r, so this first sequence is convergent to this x plus y in r, this second sequence is also convergent to x minus y in r. So therefore by product metric we can write the order pair of this xn plus yn comma xn minus yn converges to this order pair, that is x plus y, x minus y in r. So this is order pair xn plus yn comma xn minus yn is f of. So now if we apply f on this, but given function f is continuous function, so we can write this is in r, this order pair converges to this order pair in r square, because this order pair is the sequence in r square, this order pair is also sequence in r square. So this is the sequence in r square which converges to this point. So but given function f from r square to r is continuous function, but f is continuous function. Now f is continuous function means if every sequence, if we get a sequence in domain of f which convergent to some element, then the image of that sequence must converges to image of that element. But f is continuous, so we can write f of this xn plus yn comma xn minus yn. This is order pair which converges to f of this x plus y, x minus y. So this is in r. This implies, that is the required claim, that is f of x and y converges to this, implies our g of x and yn converges to g of xy in r. Hence given function g is continuous. Here Just a simple example and the important one. This is important example. Here the two functions are given. First function from r square to r. Second function is also from r square to r. G function from r square to r. But g is defined on f, that is g of xy is equals to f of x plus y, x minus y. So we have to prove that this g is continuous. To prove g is continuous, we will take the one sequence in domain of g and we will prove the image of that sequence is also converges to image of that limit of that sequence. So here x and y will be a sequence in r square such that x and y converges to r. Our claim was g of x and y converges to g of x y. That is g of x and y is defined as g of x y is defined as this. So we can write g of x and y is equals to f of x n plus y n, x n minus y n, and we have to prove that this converges to this. Now x and y n is sequence in r square, so x n converges x n y n converges to x y n r square. So x n converges to x, y n converges to y n r. So x n converges to x, y n converges to y. So addition of x and y n converges to addition of x plus y. So x n plus y n converges to x plus y in r. Also x n minus y n converges to x minus y in r. So if you take or use the product matrix space, we can write the product of these two. That is, if you take order pair this and this, so this will be the sequence in r square that converges to this point in r square. But f is continuous, so image of this sequence is convergent sequence also converges to this same limit, that is f of x and y n, x n minus y n converges to f of x plus y, x minus y. So given function g is continuous function. Now the next theorem is equivalent characterization theorem, that is three statements are equivalent. This is next theorem is equivalent characterization of continuity. Equivalent characterization of continuity. So equivalent characterization of continuity means there are three statements which are equivalent to each other. So let x and y be two metric spaces and let f from x to y be a function, then the following statements are equivalent. Then the following statements are equivalent. So this theorem can be useful to solve the examples, that is, or some further theorems. First statement is f is continuous. F is continuous at some x belongs to x. So second statement is given any epsilon positive, for given any epsilon positive, there exists some delta positive such that if distance between some x and x prime is less than delta, then distance between f of x and f of x prime, f of x and f of x prime is less than epsilon, So this is if f is continuous, then second condition holds. If the second condition holds, then f is also continuous. That is, if given epsilon positive, for every epsilon positive there exists some delta positive such that distance of x prime is less than delta, then image of that f of x prime, distance between image of f of x prime is less than some epsilon. This is epsilon delta definition of continuity. Now third statement, which is the important one, for given an open set, V, given an open set V containing f of x in y, containing the image of x, that is image of some domain in y, we can find an open set, suppose U, we can find an open set U containing x in x. So here V containing image of X in Y, so we can find the open set in X which containing X such that image of U is contained in V. Image of U is contained in V. So this third statement is important. If we have to check the given function is continuous, then if we find the open set in codomain which contains images of f of x, images of x, that is f of x, which contains all f of x in Y. So for that open set V, we can find an open set U in a domain such that which contains the x in X. Also, the image of whole open set U is subset of V. So this is suppose function from domain to codomain. Then if you find suppose this open set V which contains f of x, then for this open set V there must be some open set, suppose U in X which contains X, such that image of this whole open set U is contained in this set. The image of whole open set U is contained in this set V. There is this one is this open sphere, this open set suppose large, this is small. This is not case because here we are dealing in functions. For the whole domain, the function can be, image of function can be single element by constant function. So there is no need, that is this open sphere can be small or this open sphere can be large. This image of this whole open set is subset of image of this open set. So we can say that given function f is continuous from this function to this matrix space to this matrix space, because if we find the open set V containing all f of x, open set V in Y containing all f of x, then for that open set V which contains all f of x in Y, there exists another open set, there exists an open set in X. Suppose U is the open set in X which contains X, such that the image of this whole open set is the subset of this. Then we say that the given function f is continuous. So this is the statement of. Now this statement can be used to prove the next some theorems. So we will see that theorems in the next lecture.